Günaydın. Let me start with a few announcements. You should be following our course website on SuCourse regularly. I think you already got email copies of an announcement about textbook. You should have. These announcements are always placed on the course website. Starting from today, we will also give you homework problem assignments. I usually give those after the Wednesday lecture class. You'll find your assignments after class on SuCourse, and I'll do that starting today. So be sure to check it. You will learn from there which problems, which questions you should study in preparation for next week's discussion hours. And what are your reading assignments? Okay. Second, my office hours. I will announce them hopefully today, this afternoon. Also on SU course, I'm waiting for the schedule of my other course to be definite. I've checked your schedules, well, the general freshman schedule, and it will probably be a lunchtime hour either on Wednesday or on Tuesday, or maybe late Wednesday afternoon, when most people seem to be free, but I'm not sure about my other class, so that will be on the announcements. Okay? Then, the present version, the newly edited version of the draft notes, the textbook for this course, will be available today after this lecture at Common, if you want to get your own hard copy. And as PDF, it's already been uploaded on SU course, and you can download it chapter by chapter. Okay? If you have a hard copy already from earlier years, this is not very different, except especially the first few chapters which have been more or less rewritten, but you can use the updated PDF version on SU course. Right? Now, let me continue with the discussion of science. An important notion, an important concept in science is theory. What is theory? It is a group of concepts, group of statements that are connected systematically that purport to explain a wide area of science, and the predictions of such a theory have already been tested and verified to a large extent. But this is also very important. A theory is capable of making more predictions for new experiments under new conditions, so that these predictions then can be checked if they are true or false, and moreover, they can be used to design new experiments, to develop technology, etc. Now, so a theory is a body of scientific knowledge that has been verified a large number of times, and it is still open to checking. It's capable of making new predictions, new extensions, which are testable, and in principle those could be verified or falsified. It is important, it's important to realize that when I say theory in science or philosophically, it is different, in fact very, very different from a certain common daily life use of the word theory. When somebody says theory, when you're having a chat with your friend, it means in daily language something speculative. It is something that may not be true, something that's totally imagined, arbitrary, etc. That's what in daily life somebody means by theory. A scientific theory is just the opposite. It is not something arbitrary at all. It's something that has been tested, something systematic, and something that's capable of extension. And this mistake is made very frequently. People who discuss science publicly, who are themselves not really aware of what science is, make this mistake, sometimes deliberately. Even the previous Minister of Education in this country made a public statement saying evolution is after all just a theory. Of course it's a theory, but what he means is, by saying just a theory, means it's a kind of speculation. Who knows? Okay? The point is, it's a scientific theory, and for a scientific theory it means it's already been tested, and scientists, professionals know that as far as it can be tested, it has been tested, and it has not yet been falsified, and it can make new predictions, and new predictions of a theory keep being tested again and again and verified. So there is a very clear, unfortunate contrast in language between our daily language connotation of the word theory and the scientific meaning of theory. Okay? Now, what are some examples of scientific theories? Newton's mechanics is a scientific theory. It describes how things move, how they affect each other, how they interact, and what happens to the motion of the body as a result of it. Such a scientific theory, first of all, is not something easy to come by. Newtonian mechanics essentially developed as the main part of the scientific revolution, which is a major part of the Renaissance. Okay, it took ages. People before that, all over the world, did a lot of science. They were not totally ignorant, but their experiments were limited, their method was not explicit. And the first big general scientific theory, mechanics, which is the first thing we study in science, okay, was realized only in the 17th and 18th centuries. But then it's general because Newtonian mechanics, which we'll learn soon in the next few weeks, is the foundation of most parts of technology. All of our machines are designed based on a knowledge of this. So the fact that our technology works, the machines work, is a continuous test of Newtonian mechanics. It's a very general theory. Notice that another property of what I call a theory is that it's not specific. It is not a description of one particular machine or one particular experiment. What I call a theory is general enough, holds under a rather wide set of conditions, and it can be extended to new situations. Then I call it a theory. Okay? We already saw in the last lecture that even such a successful theory as the classical mechanics of Newton is not completely general. When confronted with the understanding of light, the fact that the velocity of light is constant, scientists, that means first Einstein, realized that this theory, in spite of all of its success, was not complete. There were things that it could not explain. And then he extended it, and we saw a simple example how velocities are added correctly according to Einstein. And what happens is, when a new theory comes, the old theory is not scrapped. It's already been shown to hold. It's just generalized and extended to a more complete, wider set of phenomena. Okay? So, our second example of a theory is Einstein's special relativity. And we already mentioned the third example, which is, again, Einstein's general relativity, which includes not just things moving at constant speed, but also things whose speed changes or are accelerated. That's also the subject of acceleration, the subject of Newtonian mechanics. How to do it properly and to take account of gravity. Okay, that's general relativity. That's an even wider theory. So general relativity contains special relativity, which contains Newtonian mechanics. Okay. Another example, very important example of a theory, is quantum mechanics. In this course, at the end of the course, we will also learn what are the fundamental properties of the quantum world. What does quantum mechanics say? I'll just mention now that without quantum mechanics, it is impossible to understand anything about the structure of matter, about atoms, about molecules, about our bodies, anything. Okay? But if you look at what quantum mechanics says, which we will learn at the end of the course, it is extremely unusual, extremely strange in terms of our daily experience. In our daily experience, we don't see directly the results of quantum mechanics. We see them indirectly all the time, because without quantum mechanics, this would not be hard. Okay? And the water molecules would not hold together. I mean, they would, of course, but I wouldn't understand how they do that. Okay? But what does quantum mechanics say? Quantum mechanics says little objects, particles, are at the same time both particles and waves. They have a wave nature. Electron is a wave. In fact, according to quantum mechanics, I am a wave too, and you are a wave, you have a wavelength. But my wavelength is so very small that in daily life, I never realize that any of the macroscopic objects around me have any wave properties. It just doesn't show up. It's too small. Now notice that a very powerful theory like quantum mechanics, just like relativity, can make some predictions, in fact, almost all predictions of quantum mechanics, which are extremely strange and difficult to understand and difficult to accept. Why do we accept them? Because they are, after all, tested, and they explain all kinds of things, including very basic things that Newton's mechanics cannot explain. This is where a scientific theory differs from ordinary daily common sense, because it's a lot more sophisticated, a lot more systematic. It can base the knowledge on experiments of the kind that you cannot do just on your own in your daily life. But nevertheless, these experiments are done by a large number of people. So notice that a scientific theory can be strange. The things that it says will sound unbelievable. This is true with a lot of modern science. Okay? However, we don't accept it just because it's a very nice sounding theory. It's a sort of popular speculation. We accept it because it has been tested. Another example of such a theory is what I brought up before, evolution, okay, which is still all over the world so much debated by the public because it's very difficult to believe what it says. And it seems to contrast some implications of religion. I say seems to. Okay? But then the question I have to ask is, has it been tested? And it has been tested many times in terms of the fossil record. And it's something that is difficult to understand because it talks about processes that went over hundreds of millions or billions of years, that gradually, by accumulation of very small changes, eventually produce unbelievably in terms of our daily experience. Big changes. Okay? But the fundamental position of this theory is that not all different kinds of living things appeared or were created or whatever separate. They are related, they have come from common ancestors a very, very long time ago. Now, we know this from, we have checked this from two different areas of evidence. The more recent one is molecular biology, which is very recent and unexpected. It developed in the 1950s. But it allows us to check molecularly the DNA, and it is, therefore we have proof that heredity, kalıtım, proceeds, the information proceeds from one generation to the other by this DNA, which is extremely complicated, and it can have very small random mutations, as evolution predicted. Moreover, now we are able to construct the genome, whole bits of DNA of different kinds of living things. Okay? And what happens? We find that things based on the fossil record and based on the predictions of evolution are supposed to be closely related. If you look at their DNA, there is a big amount of overlap in the DNA. And then scientists can work from that, predict how far back in time, 100 million years or whenever, these two species had a common ancestor. And this agrees what is found from the fossil record, so there's very strong evidence. Okay? So that makes the scientific theory in the sense that it has been verified, and it is still open to falsification, but it has not yet been falsified. It is very strong evidence. What is the difficulty in the public discussion is that it seems to contradict belief. I say it seems to because religious belief or philosophical belief is something that can be interpreted differently by different sources. So it is possible to believe religiously and to also accept the scientific theory, provided your religious belief is not interpreted by somebody literally, kelimesi kelimesine. If that is done, and if religious belief is interpreted literally as a given truth which holds about the real world, not about the spiritual world, but about the real world, physical world, biological world that we live in, then of course sooner or later there may come an experiment that shows that this literal interpretation is not true, because the experiment shows otherwise. This is what's happening with evolution. If you take a very literal belief that the world was created such and such a time ago, that all the species must have been there from the beginning as separate species, this doesn't hold against evidence. But if you say, well, this is an interpretation, it's metaphoric, and I have my religious beliefs, but they don't say something so specific about the real world, then there's no reason why you cannot be a believer of this or that religion, or an unbeliever, whatever, and accept the results of scientific research, because the results of scientific research, after all, just refer to what is in this world. Now, a good comparison about theories is, for example, with Newton, or with Galileo. Galileo laid the foundations of how motion goes on, what is acceleration, what causes acceleration, and so on. Okay? As we know, Galileo himself faced a lot of difficulty because what he said seemed to be, at that time, against the literal word-by-word interpretation of ruling dogma. We now know that that dogma was wrong, it was not the correct interpretation, whatever. Okay? But the experiment is always giving the same results. What Galileo got into trouble for was because he defended Copernicus's ideas about the solar system. He didn't even get into trouble for his own theories, but for defending Copernicus. Now we know that Copernicus is right. At the time of Galileo, when he was judged, people asked him, they found it very difficult to believe. Not everyone, but a lot of people found it difficult to believe that the Earth moves in space around the Sun. Because our daily perception is that we are at the center and we are not moving. Okay? And again, many of the opponents, people against Galileo at the time, were perfectly reasonable. They asked him the right question. They didn't say, we refuse to believe it. They said, show us the evidence. Why do I not feel that the Earth is moving? Right? And then Galileo was able, when he first used the telescope, to show, he discovered some things that he didn't even expect himself about Venus, about Jupiter and so on, which showed that all of these things were moving around the Sun and not around the Earth. And then that convinced people. Okay. So, when a scientific theory is new, for the common public, there is a big difficulty in accepting it. And you shouldn't just discard that these people are stupid, ignorant, etc. It's not like that, because of course people want, after all, everybody thinks with common sense. Okay? At least some people want to see evidence. So, if somebody says, well, it's just a theory, that is not a reasonable argument. But if somebody says, what is the evidence? That is the argument. Okay? Show me, convince me. Now, the difficulty with modern theories, like quantum mechanics, for example, scientists know a lot about the experiments that show quantum mechanics is right. But these are not the kinds of experiments that the man or woman from the public can see for herself. Because it's about the atomic world, it's very sophisticated, the experiments are done at CERN. And then the public says, oh, the CERN, they will like all, and it's difficult to get across the experiments. Galileo's advantage was, at the time the technology was simple, and the important experiment to show that Venus must be moving around the Sun just took a simple telescope. And already at that time, a lot of people, a lot of cities at least, had somebody had a telescope, so people could look, it was more accessible. But quantum mechanics is not like that. Molecular biology, looking at the genome sequences and seeing how different and how similar and in what ways is a chimpanzee and a human being. This is not something that everybody can test for themselves, therefore the public finds it difficult to believe. But you should always be very suspicious of anybody who says, don't believe this because it's just a theory. Okay? What is taken seriously in science is an argument based on what is the experiment, can you do such an experiment, what is your prediction, what is my prediction, which one will turn out to be right. Then there is a version of the argument, so-and-so is a very famous professor and he has done these experiments, he has written a book. And it says there, and I heard from my friend, though I read it in this professor's book, and the professor is very famous. It says there that this theory is right, this theory is wrong. Now this is not an argument either, because you have to say, who else other than this professor has done the experiment? Okay, so it's not on the basis of authority, it's based on the practice of science as a whole. Okay? Now, after this discussion about theory, I will go back to the example at the end of the last lecture. Remember what it was? Somebody is flashing a light in a train, and of course the light travels with the speed of light. The train is moving with velocity v2. Somebody else is observing, making an observation about this light and measuring the velocity of the light with respect to someone on the at rest on the station. Okay? And we found that the correct way to add velocities is v equals v1 plus v2 over 1 plus v1 v2 over c squared. Okay? To explain it, let me just draw a picture, it will be easier what I'm talking about. Okay, picture here. This time measures says I find a velocity v. Okay? And this is the correct formula. Newton's theory is mostly right, but not completely right. It doesn't give the right answer. Okay? When does it not give the right answer? It doesn't give the right answer for velocity of light c. But if you use this formula, if one of the velocity, for example, v2 is c, okay, then the result is also c. So it agrees with the observed experimental fact that anybody, no matter how fast they are moving or whether they're at rest, with respect to each other, measure the same speed of light. Okay, you remember that. That's what we discussed in the last lecture. At the end of the lecture, one of you came up to me and asked a very good question, which I had forgotten. Remember, I said V is approximately just our usual V1 plus V2 of the old Newton theory. Okay? If V1 and V2 are much less than c squared. And your friend's question was, what does much less mean? How much less? Because something can move with any velocity, it can move at 1/10 of the speed of light, it can move at half the speed of light, it can move at the speed of light at most, okay? But it can have anything. So how do I decide which velocity is, in quotes, small enough? Okay? Well, that depends on your accuracy. Accuracy, hata payı. Ölçüm duyarlılığı. Okay. It depends on doing this experiment or designing this piece of machinery or whatever you are doing to use the formula. How accurate you want your results to be. Plus, not just what you want, but how good are the available instruments to measure velocities. Okay? If you are doing an experiment in which the velocities are, let's say V1, let me give an example on the board. Suppose instead of the train I have something very fast that's moving at 5% of the speed of light. Okay? And a person in this fast rocket is doing an experiment in which there are some nuclei, let's say, and particles are coming out of the nuclei at speeds a tenth of the speed of light. Then what happens exactly equals V1 plus V2 over 1 plus V1 V2 over C squared, which means, okay, upstairs I'll just leave V1 and V2 because I'm not going to use them at the moment. Downstairs I have 1 plus, what is this number now? It's 0.1 times 0.05, right? Because I have here V1 over C, which is 0.1, and V2 over C, which is 0.05, so this number is just this. So the exact formula says the total velocity is V1 plus V2, but not exactly. I have to divide it by 1 plus 0.005. Right? Now, I can make the approximation it's approximately equal to V1 plus V2. Approximately, this time means not exactly, but approximately equal. I can use that if, okay, measurement needs only about 0.01. So I would use Newton's or Galileo's simple formula, just your common sense formula, V1 plus V2. If, for my purposes, whatever I want to use these particles for, their velocities, the total velocity I measure, isn't needed to be exactly known within 1% or so, then 0.005 is okay. But there's another condition. I may want to have very high accuracy, very exact measurement. But when I'm doing velocities distance gone over time, I'm using a meter stick. And the meter stick has ticks only at centimeters, 0.01. Okay? 1 meter is 100 centimeters. So I have only 1 over 100, 1% accuracy in my measurement. Then there is no sense to use a formula which calculates things containing 1.0005, because, okay, maybe that's the exact result, but I cannot measure whether it's true or not. Okay? So the answer to say, when shall I use an exact formula or an approximate formula? When are these velocities slow enough? Depends on the situation, depends on the experiment, and depends both on my design, how much accuracy do I want, and how much accuracy can I get. If I don't have the right instruments, there's no point. Okay? So this brings us to the question of error and accuracy in science. Whether you are doing an experiment, designing a machine, or writing a lab report, or solving a problem, or reading a newspaper article which says, doctors discovered that such and such a medicine works in so many % of cases, and because, etc., etc. Okay? Now, if there's a claim there that this thing works with fantastic, 10 to the minus 6, 1 part in billion accuracy, you have to think, do they have the right instruments? Can they really measure this? Something that is directly important for you as students, when you solve problems, you use a calculator, pocket calculator. You multiply two numbers, okay, you put them in the calculator. You multiply, let's say, 5.83, and, or let's say, you divide 5.83 by 2.9 on the pocket calculator. The pocket calculator will give you some number, 2 point something, something, something. It will give you 15 digits. Okay. Don't believe those digits, because you put in something that's only, 1% accurate. Of course, the calculator is a machinery, and it will give you some more numbers, because the number you put in as what I said, 5.83, it will put that, it will remember that number as 5.83000000 and treat it as if it's accurate. Okay? And it will give you a result. You put in 5.83 divided by 2.9, and you get 2.78. Of course, I'm making this up now. 5940025. Don't take all of that down in your book. If you give that to me in an exam, 1 point off. See? Whatever accuracy goes in, only that amount of accuracy comes out of the calculation. Your computer may put in some more numbers, but only take as much as you put in. Okay? Now, before we take the break, I will give you the first anket. So everybody takes a piece of paper, writes their name, just their name, okay? Small paper. I don't want a lot of writing, you don't have time anyway. This is not an exam. The question is, what did you not understand in this lecture? Okay? You answer. If there's any question in your mind that you didn't quite understand, you write it down there. If you have an empty paper, it doesn't count. So it is not just attendance, don't just write your name. Underneath your name, give an answer. What did you not understand? Alright? And then, when you are finished, I'll be standing at that door, over there. Everybody leaves through that door, gives me the paper and goes out. Nobody stays in the classroom. You all take a break for 10 minutes. Okay?